Before we begin, just a brief note for those who want, deeper material. Subscribers to the Old World Timber email list receive carefully researched ebooks, detailed videos showing real DIY woodworking projects being built step by step, and exclusive timber-focused content that, is not published publicly. The work is slow, methodical, and grounded in material reality rather than trends. Subscription information is in the description. Now to the subject itself. Modern timber is marketed as stronger, more reliable, and more advanced than anything used in the past. On paper, that claim looks convincing. Load ratings are higher. Strength values are standardized. Treatments promise protection. But the quiet truth, the one you only see after decades, is that much of what we now call stronger timber is structurally obedient in the short term and materially fragile over time. The lie isn't that modern timber can carry load. It's that strength alone determines survival. Strength and durability are not the same thing, and they never were. Modern engineering defines strength as resistance to force at a given moment. Old builders were more concerned with how wood behaved after years of moisture cycling, compression, creep, and fatigue. A beam that carries load today but degrades internally over time is not strong in any meaningful, long-term sense. Historical timber culture understood that distinction clearly, even without formulas to name it. Modern timber is optimized for predictability, not endurance. Plantation-grown trees are selected for fast growth, uniformity, and straightness. These traits make milling efficient and grading simple. They also produce wide growth rings, high proportions of early wood, and lower density fibers. The timber behaves predictably under short-term load tests, but it absorbs moisture faster, dries unevenly, and fatigues sooner under cyclic stress. Old timber grew slowly because it had no other option. Trees used in historic structures often grew in crowded forests, poor soils, or harsh climates. Slow growth produced tight growth rings and dense latewood. Now, this didn't necessarily make the wood stronger in a laboratory sense, but, it did make it more resistant to compression set, fungal penetration, and long-term deformation. That resistance is, in fact, what allowed these structures to last. The biggest misunderstanding, really, is how wood actually fails. Most long-term timber failures are not dramatic breaks. Instead, they are quiet losses of integrity. Fibers collapse under repeated moisture exposure. Micro-cracks form along grain boundaries. Compression zones lose elasticity. By the time visible damage appears, the structural margin is already gone. Strength ratings, honestly, do not capture this process. Kiln drying improves speed, not stability. Modern kiln schedules remove moisture quickly to make timber usable fast. In doing so, they lock in internal stresses. Wood appears dry and stable, but fiber tension remains uneven. Over the course of years, those stresses, release through twisting, checking, and joint distortion. Air-seasoned timber took a lot longer to prepare, but it revealed its weaknesses before use, not after installation. Chemical treatment, honestly, addresses symptoms, not causes. Pressure-treated wood resists fungi and insects, but it does not prevent moisture movement. Treated timber still swells, shrinks, and creeps, and when treatment leaches or cracks open pathways, decay begins inside a structure that was assumed to be protected. Old builders, well, they avoided this by selecting naturally durable wood and designing structures that dried quickly. Modern grading systems, well, they tend to ignore time as a variable. Grade stamps only evaluate knots, grain slope, and visible defects at a single moment. They really say nothing about how a piece will behave after, say, 30 years of seasonal change. You know, two boards with identical ratings can actually age very differently. Old selection methods, on the other hand, filtered timber through exposure and observation before it ever carried load. Engineered wood, I must say, exposes the same misunderstanding, just in a different form. Laminated beams and composites are, well, extraordinarily strong under controlled conditions. But they are also dependent on adhesives and, you know, uniform moisture control. When exposed to fluctuating humidity, glue lines age, creep accelerates, and failure modes become honestly complex and difficult to inspect. Strength is engineered. Longevity, though, is assumed. Old builders, you know, they really trusted mass and redundancy over optimization. Historic structures often used larger sections than strictly necessary. Now, this was not inefficiency at all. It was, in fact, insurance against unknown future conditions. As fibres degraded slowly, load paths would adjust naturally. But modern designs, well, they often operate closer to calculated limits, leaving less margin for material aging. The idea that stronger wood allows thinner structures, that does have consequences. Reducing section size increases the surface-to-volume ratio, which actually accelerates moisture exchange and thermal stress. Thicker timbers, on the other hand, dry more slowly but fluctuate less. This dampening effect, you see, matters over decades. Old builders accepted bulk because, quite simply, it stabilized the material. Modern timber performs well when kept dry and controlled. That's not a flaw, it's a limitation, really. When buildings remain perfectly sealed, ventilated and maintained, modern timber can perform admirably. Problems arise when those conditions fail, as they inevitably do. Old structures were built assuming moisture intrusion would occur and designed to survive it. Historical survivorship is often misattributed to luck. When we see an old beam still sound after centuries, we often credit species choice or climate alone. In reality, it's the interaction of slow-grown wood, conservative sizing, air exposure, and material respecting design. Remove any one of those factors and survival rates drop sharply. Modern builders are taught to trust specifications more than observation. Old builders learned by watching wood change. They saw which beams twisted, which posts rotted, which joints loosened. That feedback shaped material culture. Today, failures are often hidden behind finishes until replacement is cheaper than repair. The learning loop is broken. This doesn't mean modern timber is useless or inferior. It means it is specialized. It excels when used within its limits. Problems arise when modern strength claims are assumed to equal long-term resilience in uncontrolled environments. Strength is a snapshot. Durability is a story told over time. The biggest lie is not malicious, it's incomplete. Modern timber is strong by modern definitions. What's rarely said is that those definitions prioritize short-term performance, standardization, and efficiency. Old builders optimize for survival, repairability, and material honesty. They were solving a different problem. Understanding this changes how you assess old and new structures. When a modern beam cracks, it's often treated as a defect. When an old beam compresses and settles without failing, it's often overlooked. One resisted force, the other adapted to it. Both tell you something important about wood. The material itself hasn't changed. Wood still responds to moisture, load, and time exactly as it always has. What has changed is how much patience we give it and how much movement we allow. When those are removed, strength numbers become a poor substitute for understanding. Historical timber knowledge isn't anti-modern. It's corrective. It reminds us that performance over decades matters more than performance on paper. That structures exist in weather, not laboratories. That material behavior does not care about marketing language. If we want timber structures that endure, we have to stop asking only how strong wood is and start asking how it ages. Old builders never separated those questions. That's why so much of their work still stands. Understanding timber behavior is not nostalgia. It's practical literacy. It informs how we select wood, design joints, allow movement, and judge claims about performance. If this kind of historically grounded material-focused knowledge matters to you, consider subscribing to the Old World Timber email list. The future of building durable structures depends on remembering what strength actually means.